no cases where we have anti-gravity or repulsive forces. This is actually a vector force, and it's in the direction, of course, of attracting 1 to 2 or 2 to 1, so that this is an attractive force. For example, if we have two masses, M1 and M2, then of course M2 will pull on M1 straight over there, directly towards this other particle. And M2 is pulled by M1 directly in this direction. And these two forces that accelerate these masses are given by this equation. In this equation, G is a universal constant for the whole universe, and it has a relative strength of about, this force, of about 10 to the minus 39th. I'm going to compare these different forces roughly. Now, near the surface of the Earth, if we think about the Earth and think about an object that's near the surface of the Earth, then the Earth is so large, 4,000 miles in radius, that a few feet or a few hundred feet, in fact, really don't make much difference. The actual equation would be to compute the mass of the object and the mass of the Earth, and the distance between the two is capital R, the radius of the Earth, and that would give us the force between the two using the universal gravitational constant. But it turns out that this force of gravity near the surface of the Earth is equal to a constant G times, which is the acceleration, times the mass of the particle. This is a very, very important expression, especially in fundamental physics, because it gathers together in G, the acceleration, all of these other terms except for one of the masses, as we'll show later. So each object has a downward force toward the center of the Earth, such that if it's twice as massive, it'll have twice the force, and therefore everything falls with the same acceleration, because you recall that that m times g, the gravitational force, is going to equal to m times the acceleration for that object. Consequently, the acceleration is always equal to g. And g, as we've mentioned already, g has a value of 9.8 meters per second squared, which you must memorize, or approximately 10, or 32 feet per second squared, which you also must memorize. We will use 10 for most of our problems just to give us a fast calculation. That's the gravitational force. It's the weakest of all the forces. It affects every mass and even pulls on light itself, as we'll find out. Then there's the weak force. The weak force is probably the least understood historically, at least by the lay public. It has a strength of about 10 to the minus 14th. So it's much, much stronger than gravity. Gravity is incredibly weak. In fact, in all of the particle physics, we can actually neglect gravity until we deal with problems that have to do with things like black holes or enormous stars. And this weak force involves leptons and neutrinos, and it's a very short-range force. By contrast to that, the gravitational force is what we call infinite range. It has an infinite range. That means a mass here on Earth, such as this pencil, will be pulling on every particle that's on a distant galaxy at another part of the universe. There's no end to this, because if you look at this expression, 1 over r squared never vanishes. Although r gets very, very large, the force gets very small, still the force has an infinite range. This has a very limited range. And it's still relatively weak, except for the gravitational force by comparison. It actually arises when we have a particle like a neutron, and a neutron will decay into a proton, an electron, which is negatively charged, and an anti-electron neutrino. And when you have these neutrinos that are involved and the leptons, then you can almost rest assured that this is going to be a weak force somewhere that's involved in the production of this object. We'll say more about this weak force much later in the second semester when we talk about the fundamental forces. Something that's far more important to our everyday lives, like gravity, are the electric and magnetic forces. Everyone is familiar with electrical forces and certainly with magnetic forces. So we can say, and we now understand these two as two manifestations of the same thing, which we now call the electromagnetic force. And it has a strength of about 10 to the minus 2. Incredibly strong by comparison to the weak and gravitational. In fact, if you look at this minus 2, the gravitational force by comparison, the electromagnetic force is 10 to the 37th times as powerful as gravity. So you can see that it's of enormous power. Well, the electric and magnetic forces always involved charged particles and currents. It has an infinite range also, and the strength of about 10 to the minus 2. I want to write out what the force is electrically. The force due to the electrical attraction of two particles is called the Coulomb force. Coulomb force. The Coulomb force is given by a constant K, very similar to this equation here. I probably should put a box around this. K times the charge of the first particle, charge of the second, divided by the distance between them squared. Here, charge, electrical charge, plays the role of masses. So if I have two charges, Q1 and Q2, then they can attract one another or they can repel one another. When do they do which? Well, it turns out that like charges repel and unlike charges attract. So positive attracts negative and negative attracts positive. This is very different from gravity, where all the masses are positive and the force is only attractive. We do not yet know if there's anything like a negative mass in the universe, which of course would exhibit an anti-gravity. Here we do have both attractive and repulsive situations with this Coulomb's law. Coulomb's law is, of course, of incredible importance in physics, and this constant K has a value of 9 times 10 to the 9th to relatively good accuracy. And so we can use this 9 times 10 to the 9th to calculate the forces between two charges. The charge here is measured in units of coulombs, and that's the unit of the electrical charge. So we have a coulomb times a coulomb divided by a meter squared, and K will convert that to a force in newtons. Now, if we have a particle that's moving in an electromagnetic field, I've written the force that it will feel on any charged particle as charge times the electric field plus charge times V cross B, and this is the cross product we discussed recently that involves the sine of the angle and the right-hand rule, and that's where this comes in that's so important. We'll, of course, discuss these laws very extensively in the first part of next semester. In fact, the second semester is primarily spent, at least half or about half of it, is spent on understanding the very important phenomena of electricity and magnetism. So we have two equations that arise from the electromagnetic force, the Coulomb force, which gives us the force here, and the concept of the force due to an electric field. Now we could set this and say, well, this is going to be equal to mass times acceleration. And this is called, actually, has a name, it's called the Lorentz force. The Lorentz force equation right here. And so we haven't gone into the details of saying how do we define the electric field, how do we define the magnetic field. But if I have those two fields, then to take the electric field with a charge Q in it, it'll feel a force Q times E. If I have a charge in a magnetic field that's moving with a velocity V, this will give its force. So this force works very generally, and this is an incredibly important equation. We would set it equal to mass times acceleration to find out how a charged particle accelerates. Notice again how similar this is to the equation for gravity. And they're both infinite range forces. The last force is very interesting because it's what we call the strong force, or nuclear. This is the force that holds the nucleus together and has a strength of about 1, maybe up to as much as 10, somewhere in this range. So it's about 100 times as strong as the electromagnetic force. The nuclear force, we don't have a nice equation for it, and we don't have for the weak force here either. But this nuclear force is the one, if we look down inside the atom, got all these electrons, you know, as you remember from your high school science class, moving around. And down inside there, there's a nucleus. And these electrons are negatively charged. The nucleus is positively charged, consist of very heavy particles, protons, which are positively charged, and neutrons, which are neutral. These are both, have a mass of about 1,800 times what one electron has. And there are as many of these protons as there are electrons. So almost all of the mass of the atom is contained in the nucleus. Now, these protons are held together with neutrons in the nucleus by what is called the strong force. Now we have understood with our newest theories that the proton and the neutron itself are held together are made of more fundamental particles called quarks. And these quarks are held together by particles called gluons that jump back and forth among them. And as these move around, this would be a single proton or a single neutron. Collectively, they're called nucleons. And these quarks, there are 3 of them in the proton and the neutron, they are bound extremely tightly in here, and they're bound by the strong and nuclear force. So these are our forces: strength of 1, 10 to the minus 2, 10 to the minus 14th, 10 to the minus 39th. Very short range, only across the nucleus, about 10 to the minus 15th meters, what's called a Fermi or a femtometer in distance. This has an infinite range, again, very, very short range, again, an infinite range. Those are the things to remember about these 4 forces. And now you might say, well, what about a spring force? What about, you know, the force that a rope is pulling on something? Those are all made up from compressed matter. And we're really looking at the compression of electrostatic forces. So they are all built up of these electromagnetic forces. But there's some other forces, what we call artificial forces, such as centripetal force that we'll get to shortly. In this next section, I want to talk about some derivative forces. These forces are basically derived from the other forces in different ways. The first of these is what we call a frictional force. The frictional force is something we're all very familiar with, because if we try to drag something across the floor, it resists. Here's an object, and we're going to put a force on that, and we're going to drag it across the floor, and it has a frictional force. It's going to push back as we push this way. In fact, if we're pulling this thing with a constant velocity, then we're applying a force here all the time that exactly balances this force back here in order to get that constant velocity, aren't we? So if this velocity is constant, it means the force that we're pulling with is equal to the frictional force. And that tells us what those frictional forces are. Actually, there are 2 kinds of frictional forces, static and dynamic. Many of you are familiar with the fact that once you get something moving, it's easier to keep it moving. So the static force of friction is always greater than the dynamic force. Static means, okay, that crate is sitting there, and I've got to get it moving.